time and joining us here today. This class, the Acoustical Engineering BE 531 and 32, this is the kind of culmination of that two-class, journey that our students have been on. For this second quarter of the class, they've had a class project that is exploring some area of ultrasound diagnostic imaging, and it's our pleasure for them to share with you some of their work, and hopefully you learn and see some of the exciting things in ultrasound that we've covered these past 2 quarters. And so our first presenter will be Ruben, who will be exploring nonlinear pulsing sequences used to image ultrasound contrast agents / microbubbles. Ruben?
Hi, everyone. For this paper, I'm going to be presenting a frequency response to low mechanical index pulse sequences in contrast-enhanced ultrasound. Contrast-enhanced ultrasound basically consists of microbubbles injected directly in the bloodstream. This solves a key limitation in Doppler imaging, which is the low velocity of the blood in the microvasculature. So the nonlinear response of these bubbles help us enhance these signals, and it can help us differentiate. For example, in this first picture, where we can see it as if there was nothing wrong, and in the second one, when we use contrast-enhanced ultrasound, we can see that all the microvasculature at the edge of this lesion, it's not going in there. So it can help us differentiate all those clinical problems. Low contrast techniques, which is the ones I'm going to be exploring, can give us a real-time imaging. It can help us measure stable harmonics, which high mechanical indexes techniques sometimes can disrupt these bubbles. So we are going to be using these low mechanical indexes techniques, and they do not disrupt the microbubbles and improve the contrast. It has some drawbacks, which is reduced penetration, and they are a little bit less sensitive. But anyway, I'm going to be specifically taking a look at inversion, pulse inversion, and amplitude modulation. Pulse inversion consists in 2 pulses, one positive, one negative. The linear response is going to be the same for both, but the nonlinear response, which is going to be basically from the microbubbles, is different. It responds differently to positive and negative pulses. So we are going to be getting a nonlinear response at the end, and this type of imaging cancels out the odd harmonics and lets us preserve the even harmonics. For amplitude modulation, we get 2 positive pulses in this case, but it's going to be different in amplitude. One is going to be a full wave, and the others normally at half wave. When we subtract them in the pulse inversion, we sum them up. In amplitude modulation, we subtract them, and the linear response is going to be cancelled out, and we are going to be just left with a nonlinear response. The proposed method here, in this case, we did a simulation. I did a simulation based on another paper, and it's a plane wave generated over bubbles in a domain, and we're going to get a response from the Rayleigh-Placet equation. This equation basically consists of pressure, the material from the bubble, the shell, and the radius. And we're going to be taking a look at the radius over time. And when we solve for this radius, we can generate a final RF signal. In this case, we took a frequency of 1.7 megahertz, which is close to the resonant frequency for a 2.4 micrometer bubble. And this was taken because the transducer bandwidth is between 1.4 and 3.6, so we can take a look at the first and the second harmonics. And for our results, in the first part, we can see that we have a positive and a negative pulse, the positive being the blue and the negative the red one, and we get in the middle a green nonlinear response from the bubbles. For the frequency response, we can see that the first harmonic are canceled and the second harmonic is really enhanced, so we can take a look at that comes basically from the nonlinear response from the bubbles, and we can really enhance those signals. For the amplitude modulation, we can see the two pulses but in different amplitude, and the frequency response is a little bit different as we can take a look at all the nonlinear response in all the harmonics, not only in the even ones. And yeah, this gives us at the end a better view of the microvasculature and the independent of the velocity that is going to be going through it. Yes, that's basically. Thank you.
Next, we're going to have Mike, who's going to be talking about some of the work actually from my lab down at the U and some kind of more recent approaches to imaging microbubbles from what Ruben was talking about. So it's a nice follow-on talk from Ruben.
Thank you. Right. Hello everyone, my name is Mike Lehman. Thank you all for coming. Today I'm going to talk to you about nonlinear ULM features of the microvasculature. So nonlinear ULM is another methodology for visualizing the microvasculature, especially at the resolution level, and it's just a super high resolution of the microvasculature. For this project, we're working on quantifying some more of that, of perfusion level, low blood flow, specifically looking at projections or velocities from 1 to 25 and 25 to 125. The smaller the number of the projection, the lower the velocity. Some background here. Traditional Doppler, we're able to visualize blood flow, but we can't see low blood flow because we have tissue motion that overlays our blood flow. We have to use a high pass wall filter to remove that. And so we aren't able to actually look at any perfusion data there. For conventional ULM, or traditional ULM, uses linear pulsing sequences, and again, we can visualize the vasculature better, but similar problem, we have our tissue motion overlaying our low velocity blood flow, high pass wall filter removes that, can't look at blood flow perfusion. So finally, nonlinear ULM, utilizing either pulse inversion or amplitude modulation pulsing sequences in order to actually separate our tissue motion and our blood flow velocities. And then we utilize the SVD in order to actually separate those velocities in general. And so typically we have, once we rank our singular values from high to low, we'll have our low end there showing our perfusion data, followed by our medium flow and our fast flow data, and then ultimately getting into the noise. And so again, for this project, mostly looking at perfusion and median flow. For the methods here, I was given a data set from the lab from a previous project of a rat's spinal column at C5, imaged at 400 hertz, and it was amplitude modulated, 5-angle pulsing scheme at 400 hertz there. The data processing side, once the raw IQ was given, we registered the IQ data, SVD filtered, equalized the noise, NLM filtered, localized the bubbles, and finally do the tracking. And from there, looking at our XZ plane or the azimuthal plane, trying to see bubbles that aren't moving very much within that plane to indicate that they are traveling mostly through the elevational plane only. And looking at their phase and their backscatter amplitude from that. This first image here comes from the paper where I got the original data from, and the main takeaway from that paper, or not the main takeaway, but one of the takeaways from this image from that paper actually showed some quantifying some data that if there is damaged tissue compared to non-damaged tissue, the track length of the perfusion tracks decrease. And so from that, we can also see that the track lengths are usually between 30 and 55 micrometers as well, which is roughly the range I was looking for within my data set here. Going on to the rest of my data sets, I have two separate sets, one at the first set being in the low blood flow, so low velocity blood flow from 1 to 25 SVD, and then the medium data set from 26 to 125 SVD range as well. Looking at the backscatter amplitudes, the R0 phase or power, and looking at the mean phase change and phase variance of those bubbles. And from this, just found a range of various mean phase changes and phase variances for all these bubbles here, and plenty of different profiles as well for the backscatter amplitude. Another thing to note with that, we did not notice any correlation between the backscatter amplitude and the phase variance. And a couple examples here show we have similar profiles for these backscatter amplitudes. However, our phase variance is like right here 0.1, and the bottom one is 0, and that's similar for the medium flow as well. So more research will need to be done basically for all that, and hopefully in future times we will actually look more data sets in general, and especially looking more into the backscatter amplitude in conjunction with phase and phase variance. Thank you.
All right, so our next speaker will be Charlene, and she'll be looking at, we were talking about wall filtering or high pass filtering with Mike, and she'll be talking about exactly that again, but without microbubbles. So this is just straight backscatter from blood with imaging blood flow with ultrasound. Take it away.
Thank you. Hello everyone, my name is Charlene Kiloy, and we're going to talk about clutter filters adapted to tissue motion in ultrasound color flow imaging. So as we all know, the Doppler blood flow measurements does not only consist of the blood flow, but it also consists of a clutter that is from the tissues and also the noise. So my project is basically to form filters that are adapting to the tissue motion so that you can be able to image color flow effectively. So in rapidly moving blood cells, they have larger Doppler shifts than the slower moving tissues, where high pass filtering is used to separate out the blood flow signals. And this is mostly important because, for example, if you're trying to image the heart, where we have a lot of muscular movement and we want to estimate the blood flow in the capillary beds, it's important to be able to understand the blood flow in the low velocity sections. That's why this project is important. So in this project, we investigate an adaptive approach to moving tissue signal and improve the segmentation of blood flow and the clutter signals. So our RF signal path is that we have the scan line, then we pass it through the filter, the wall filter, and the autocorrelation, where we'll be able to display our signal. So for this project, we have an estimation of the clutter mean frequency given by R1. Then we downmix the Doppler signal by the clutter frequency. So essentially, our conventional imaging, we usually have the signal, then we pass it through the high pass filter, then we are able to go through the rest of the display. But for this part, we wanted to downmix the Doppler signal by the clutter frequency before passing it through the high pass filter. So in the stop, and therefore we'll be able to move our clutter signal back to the stop band of our high pass filter, and we'll be able to have a higher volume of the blood flow velocities. So for the simulation, we have different signal modes where we have no flow signal that is made up of the clutter and the noise, And also we have the clutter, the noise, and the flow signal. So for this project, I used the synthetic clutter and blood signal generated by applying the Gaussian mask to the discrete Fourier transform of the different samples, and we were able to obtain different curves as observed above. Therefore, for the stationary tissue with the flow signal, as you can see, we have the clutter, we have the blood, and also some noise. And for the moving tissue, we have the clutter. The center of the clutter is, as compared to the stationary tissue, is way on the side, and that is what we want to get rid of. Then for our shifted tissue, as observed, we were able to shift the center of our clutter signal back to the stop band of the high pass filter. Therefore, we'll be able to have a higher velocity. We'll be able to estimate the velocities in the lower region. And this can be quantitatively observed using the histograms, where the blue histograms represent the no flow signal, and the red histograms represent the flow signal. Therefore, as observed in the stationary tissue, there is not much of an overlap as compared to the moving tissue, and that is what we want to prevent, because if you have an overlap of the moving tissue and the blood flow, therefore we'll not be able to accurately estimate the blood flow velocity. And on shifting the center frequency of the clutter back to the stop band of the high pass filter, we were able to almost improve the segmentation of the blood and the segmentation of the clutter. And we have our area under the curve, which kind of estimates what is happening here. So for example, ideally, the area under the curve it's supposed to be in an area of 1. Yes, so when we shift the center frequency of the clutter, we were able to improve the area under the curve as compared to the moving tissue. So the tissue movement creates Doppler shifts that leak into the passband of the wall filter, and that is what we want to avoid. And this corrupts the group which has blood flow signal, leading to overlapping histograms and degradation of the area under the curve. Therefore, mixing the Doppler shifts created by the tissue motion back down into the stop band of the wall filter improves the tissue suppression and improves the blood flow detection and the area under the curve. Sorry about the whole thing. So for our future work, we want to be able to further adapt and account for the clutter bandwidth changes, and also to investigate newer matrix approaches like singular value decompositions as described by Mike. So in summary, down mixing the color flow signals by an estimate of the tissue Doppler shift before wall filtering can improve the detection of blood flow in moving tissues, and the limitations still exist when tissues accelerates increasing tissues Doppler's bandwidth. So that's my presentation for today.
Our next speaker will be Sajita, and she'll be exploring a very interesting topic, and that is trying to anti-alias our Doppler ultrasound acquisitions. So, Sajita, thanks.
Hello everyone, my name is Sajita, and my project is, the topic cannot be seen, but that's okay, I'll just tell. So my project topic is it's estimating and detection and correction of aliasing in ultrasound Doppler using 2D autocorrelation method. So first, many people might not know, but as Shalin has already explained, so in the Doppler what we do is that we send out pulses, and then at PRF and then we assess the Doppler shift within the range of minus PRF by 2 to PRF by 2. So what happens is that sometimes like it can exceed the limit of PRF by 2, which is also called as the Nyquist limit, and then aliasing can happen. So now the conventional Doppler method uses 1D autocorrelation method, so which takes into account only the phase. Now both the Doppler and the color flow that you can see here, Charlene already explained the color flow part, both are taking into account the phase estimation. So in Doppler case, what happens is that we estimate the phase, and that correlates to that helps us in correlating and then determining the velocity. In the color flow, the phase estimate maps on to the color display, and that gives us information about the velocity, the direction of the flow from the color display. Now 2D autocorrelation, but this extends on this idea of 1D, but it takes into account the phase and the temporal shifts. And also, like since it is taking into account this details, so that's why estimating of the blood velocity, it gives comprehensive detail and estimation becomes easier. So if you see this formula, so this is the autocorrelation formula, and correlation is calculated based on, it is done by summing up on the depth. M is the depth and then the slow time, and m, m is the signal at a specific time and specific depth. This is just the x conjugate. So what we do is that we take the max value of this 2D correlation that we have calculated, and that maximum value we are denoting it by tau max, and this value helps us in estimating the correct velocity, which when in case of aliasing you can't do using 1D autocorrelation method. So now I've done the simulation of single scatter, and as you can see, these are the parameters used for the simulation. The transmit frequency is 2 megahertz, and the PRF value that we should take note of is 4000 hertz. So based on this simulation, these are the results that I've achieved. So the first one that you can see, it shows the Doppler RF with depth versus the slow time. As you can see in the resulting spectrum, as the velocity 0.25 meter per second was within the system parameter range. So since it was within the limit, so it is displaying the shift in a correct manner. But on the right hand side, as you can see, the velocity value that was considered for 1 meter per second, that exceeds the limit, and that's why it got shifted onto the other side, because of the aliasing, and that's why it's not giving out, it's giving an incorrect value. This one shows the autocorrelation illustration. As you can see, so here the tau is the depth, and r tau comma 1, so that is nothing but it indicates the first leg in the phase dimension. So here basically what we are doing is that it averages and then sums up all the phase shifts over ensemble. This peak that you can see, that corresponds to the temporal shift between the two RF pulses. Here this is the non-alias case where approximately 20 samples is been used, and that is there, and approximately this is the alias case where around 60 samples are there. Now interesting part is, so this is the result of non-alias and alias case, where with the 1D and 2D, if you see, both can detect very correctly the non-alias part because it is within the range. But however, in the alias case, the 1D is showing incorrect value because it has exceeded the limit, and while the 2D has correctly shown the alias part which exceeded our PRF by 2, like I mentioned, the Nyquist limit, so it exceeded that value, but it has displayed it correctly. Now this is the thing that this factor of like this value, this helps us in understanding like where exactly the aliasing occurred and by what factor that we can take into account to correct the aliasing. Now this is an in vivo illustration that shows like how a corrected spectrum would look like if we take into account. Now we know like how we can take that factor. So if we take into account so how we can correct the spectrum from an alias case. This is an alias spectrum, and so the future work includes maybe this is just an illustration of the in vivo data. Maybe more we can use the 2D autocorrelation method on the in vivo data and see like computationally how it is working on the system. So in summary, I would say that since 2D autocorrelation, it is considering both the phase shifts and also the taking into account the temporal shifts. So it is gives correct estimation of the aliasing, and as you have seen from earlier and this data, like it provides a better way of correcting the aliasing. So yeah, and compared to the 1D and the other approaches. Similarly, like as I've already mentioned, for the future work, maybe it requires more computation, but that's the future work, and we have to see how it works. So thank you. That's my project. Thank you.
So our next talk is by Sarah, and we're taking a slight turn in ultrasound going to B mode, and how on ultrasound systems we deal with the ever-present multiplicative noise that we have on our images caused from speckle. And she's going to tell you more about the origin of speckle and how we can filter for it.
Can you check us screen sharing?
Oh, screen sharing. Screen sharing is paused. So how do I unpause?
Just stop
Go
sharing,
to
reshare probably.
Stop sharing. Okay.
Isn't it this way start doing it?
This one.
No, button
The-
below.
This one?
Yeah.
Okay. How's that? Is that good?
So
Okay. Cool.
hello everyone, my name is Sarah and I'm going to present my project, which is about speckle noise reduction in ultrasound. So for those of you who might not know, speckle is a typical noise-like pattern that you find in ultrasound images, which you can kind of see in this image. And it might look like noise, but it's actually due to small irregularities that you find in tissues. And if there's a high amount of those irregularities, the backscattered signal will overlap constructively and destructively, which is what ends up causing the speckle pattern in the ultrasound images. A speckle can reduce the contrast in ultrasound images as well as hide image details such as lesions or cysts, which is why often it's desirable to reduce speckles. However, as mentioned, since it's not actually noise, but it is part of the tissue, it's normally not, or it's not wanted to smooth out all the speckles. The most common methods to reduce speckle is compounding and image processing technique, and the challenge with image processing techniques is to only reduce the speckle while to maintain and not blur the edges of the image structures. So in this project, I implemented an algorithm to reduce speckle while hopefully preserving the edges and the image structure. You can see a rough overview of my algorithm here. So the first step was to decompose the input image in different layers with the Laplacian pyramid, and then each level is filtered separately with bilateral filter before being recombined to form the output image. And what the Laplacian pyramid does is essentially create a set of bandpass images and one low-pass image. You can see an example here of a 3-level pyramid, which is the number of layers I used for my algorithm. So as you might be able to tell already, in the lower levels, there's going to be the high-frequency component of the image, And in the high level, it's going to be the low frequency component of the image, which is why using Laplacian pyramid and speckle noise reduction is so useful, because speckle has high frequency, meaning that the lower levels are mainly going to contain the speckles, while in the high level it's mostly going to be the image structure. This enables us to apply higher smoothing and more blurring in the lower levels, while applying low amount of smoothing in the higher levels to preserve the image structures. So with the actual filtering, I use bilateral filters, which creates the output image by weighted summation of the neighboring pixel. How much a neighbor is going to contribute to an output pixel is depending on two factors, the first one being the spatial difference. So the closer a neighbor is to the current pixel we're looking at, the more it's going to contribute to the output. And then the second factor is the intensity difference. And the idea behind this is that if you have a sharp edge, for example here, look at this point, it's going to be a high intensity difference to the other pixel. So if a neighboring pixel has a high intensity difference to our current pixel, it's not going to contribute much or not contribute at all to the output. That way we don't have blurring if there's a sharp edge, but on the other hand, if there's only like small variation in intensity, it's going to get blurred out. So for both the spatial and the intensity, we have to choose two thresholds that decide how much smoothing is actually going to be applied. And for the spatial threshold, I did this by trial and error. And for the intensity threshold, I calculated it for each layer, depending on the median absolute deviation of the gradient of that layer. In both cases, I have higher threshold values for the lower levels so that we have more smoothing, and then lower values in the higher levels of the pyramid to keep the image structures. The first image I tested my algorithm on, I simulated with mask to represent two lesions with speckles, and as you can see on the right image, the algorithm does reduce the speckles while maintaining the shape of the lesions. This makes the speckle SNR and the contrast to noise ratio go up as the speckle variance goes down. However, the actual difference between the lesion and the background unfortunately doesn't go up, it actually decreases slightly. And then I also tested my algorithm on some real ultrasound data. On the left side it's the noisy images, and on the right side the filtered images. And as you can see, it does smoothen out the speckles while preserving the image structure. So, in summary, the algorithm does what it's supposed to do. It smoothens out the speckle while preserving the edges. However, there's still room for improvement, especially since it didn't actually increase the contrast between the lesion and the background. So, for future work, the first step would be to test the algorithm on more data. I only tested it on a very limited amount of data here, so it would be good to see if it actually works on a high amount of different variation of pictures. Then when it comes to actually increasing the algorithm, the first step would probably be to use different window size with the bilateral filtering, so different neighborhood sizes. Currently I use a fixed number of 11 by 11 for each layer, but if you look at the pyramid layer, the resolution actually decreases, so it might be beneficial to use different window sizes depending on the layer. Another option would be to use adaptive window size, which is calculated depending on image characteristic. Another way of improving your algorithm could potentially be to choose different filter parameters or different filter thresholds based on additional or completely different image characteristic. Or instead, if there's a good objective evaluation method, all the parameter filter and potentially also the amount of pyramid layer could be chosen with a machine learning application.